let's compare that to the steroid hormones. They're real straightforward, right? They're all derived from cholesterol. They have a long half-life. They transport it down to carrier proteins. They have cytoplasmic or nuclear receptors. They give mostly genomic effects, meaning that they trigger gene expression. Obviously, you don't need to memorize this. This is not a biochemistry class. If you think about chemistry, I should do this. But I just wanted to point out how similar some of these are. Here's cholesterol, and you can look at it, all except for this little hydroxyl group right here, it is nothing but hydrocarbon. So just this little hydroxyl group gives a little polar piece right here, but it's mostly hydrophobic. Now you'll notice that our goal is to produce hormones that will trigger some response from this, right? This is all, like I said, this is going to be occurring in smooth ER. And you'll see that some of these hormones, like aldosterone is a hormone that we'll study when we study the urinary system that is important in regulating blood sodium levels. It causes our bodies to reabsorb a lot of sodium. Cortisol is a hormone that's important in the inflammatory response and in inflammation. In fact, too much of it's not a good thing. I don't know if you were aware of that. Stress induces the production of cortisol. So does being overweight and things like that. It causes a lot of inflammation in the body that we don't really need. Estradiol is the most common form of estrogen. And you'll notice that there are a lot of crossovers in these pathways. We can take cholesterol and make a lot of different intermediates, and we can make from it progesterone, or we can make from it an intermediate in testosterone production. And you'll notice that even if we made progesterone, progesterone can be converted into testosterone. They're very similar. Once we have testosterone, testosterone can be converted into estrogen. Very similar mechanism. Or we could take progesterone and convert progesterone into aldosterone. Or it could be converted to this intermediate pathway into cortisol. So these things are all related. And what's interesting, unfortunately it doesn't have the structure of a lot of these on here. But you can see, let's just focus on these two here. These two right here are incredibly similar to each other. What's different about them is this right here. Okay. There's a little carbonyl group right there that's different. This one doesn't have it. What they do for the body, incredibly different. So this is how important that specificity is, right? It's just a little thing like here, like a little double bonded oxygen here and not over here, can create a drastically different response because it'll bind to different receptors. Okay? So that's all there. Just specificity, affinity, really important in ultimately triggering the response because the signal has to bind to